I wanted to talk to you a bit today about impulse graphs because I find that's where people run into some of the most difficulty, but also um, it it lends itself or it's very closely connected to what you learn in Math 31. Are any of you in Math 31 this semester or planning on taking it in the future or have already taken it? Okay, so a few of you have taken it. Um, in their last semester of high school. It's typically a final semester of high school course. It's not part of Physics 30 to learn calculus, but Newton invented calculus for physics, or so I like to claim. And so a lot of physics is secretly calculus, and we just don't tell you that as we're teaching it. So I wanted to show you a little bit of how this connects. So if I have a force versus time graph, and let's say I have a constant force for a period of time, we know that impulse is F delta t. And so impulse can be found from the area under that graph. Which has a height F and a width delta t. So it checks out. The area of that rectangle is F delta t, and the formula for impulse is F delta t, so impulse is the area of that rectangle. But in real life, objects don't tend to turn on the force and then turn off the force. That's not really how the world works. A force will gradually start and gradually stop. So a realistic force versus time graph would look more like this. It would be curved. It would gradually begin and gradually end, and that I think makes more sense. However, this formula, the F delta t, won't work in that case because it's not a rectangle. And F delta t describes the area of a rectangle. And so instead we say impulse is the area under an F versus t graph. And that does not look like a good shading. Oh well. I'm going to just shade it with my pen. So impulse would be that area. There's no formula to calculate that area. It's curvy. It could be anything. The force can be totally random. And so that's when calculus comes into play. So imagine I measured just one little tiny rectangle, like that. I could calculate the area of that rectangle. And what if I just made a whole bunch of little tiny rectangles? I could calculate the area of those rectangles. The area of each rectangle would be area equals the force at that spot times the little delta t. So that's the area of a little rectangle. And the area of the whole shape would be the total impulse, would be the sum of all the little areas. So all the little F delta t's. Now in calculus, that kind of summation, the summation of little tiny rectangles, is called an integral. Do you guys remember integrals from calculus? And do integrals make you shudder when I say the word? Integrals are an integral part of calculus. Haha. And so we would write that in calculus terms as impulse equals integral f dt, instead of delta t, because d indicates that our delta gets very, 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 very small. And d in calculus means super tiny. And the little S shape is our integral symbol. And it just means you're summing up a whole bunch of little tiny rectangles. So it's just a fancy summation symbol for little things. All those rectangles added together make the area under the curve. However, you guys aren't in calculus this semester, and Physics 30 pretends that you guys don't have any calculus knowledge, and so we're not going to do that to you. That's why you won't have any curvy graphs when we do impulse graphs. The graphs that you are going to have are triangles and rectangles. And I'll make a nice trapezoid there too. There we go. That's the kind of force versus time graph you're going to encounter. You need to know that this isn't a realistic force versus time graph. Nothing in physics is a straight line. It just can't be done. It's force doesn't instantly change. It breaks the laws of physics, in fact, because it sort of breaks speed of light rules. Things can't instantaneously change. But this makes the math easier, because you just have to calculate the area of triangles, rectangles, and little triangles. So the area under this curve would be shape 1 plus shape 2 plus shape 3 plus shape 4. But be super careful when you're doing these kinds of calculations, because 2 is a negative area. And negative areas get subtracted. So one of the common mistakes I find in impulse graphs is this. There it is. I might have a curve that looks like this. And this is force, and this is time. And it will ask you, well, what's the impulse on this graph? Trying to get the picture back. There it is. So a lot of students will be like, well, clearly the impulse is the area under the curve. So the impulse is that. And that is sadly very wrong, because the y-axis goes on forever and ever and ever. If you keep on going underneath the curve, you're going to end up getting infinite area, and that doesn't make any sense. And so instead of going the area under the curve, we should be looking for the area between the curve and the x-axis, which is this really poorly drawn rectangle and this littler rectangle, where we have a positive area and a negative area. So anytime you see the shape of an FT graph drop below the x-axis, you should be looking for a negative area in your graph. So I'm going to do an example, probably the worst of the examples. And I'm going to see if I can remember even how to do this one. So I'm going to label this point F max. And let's call this 1, 2, 3, 4, 5, and it's time in milliseconds. Pretty sure this is one of the assignment questions, or close to it. And it asks something like a 10-kilogram car, which doesn't really seem like a car now that I think about it, but I'm just going to go with it. changes speed by 20 meters per second while experiencing a force. This is its graph. What is F max? So this is a kind of question that you might find tricky. It's got a bunch of the things that tend to catch students by surprise. I need to warn you that I'm making up this example as I go. In future sessions, I might have examples more prepared. That's why it's going to make no sense. Like cars aren't 10 kilograms. It's probably unlikely to change its speed by 20 meters per second in 5 milliseconds. But let's just go with it. So clearly the impulse is the area of this triangle. At some point, junior high teachers taught students that triangles are 1/2 base times height only if it's a right angle triangle. Or somehow that gets caught in a lot of people's heads, but that's not actually true. The area of a triangle is 1/2 base times height, no matter what triangle you're looking at. So in this one's case, our height is F max, and our base is 5 milliseconds. And I've deliberately chosen to do milliseconds because I think there's an example like that in the assignment that gets everyone. So make sure you check your axis labels to see what units you're actually working with. So we're going to use the impulse momentum theorem, which says impulse equals change in momentum. So we have impulse equals m delta v. And our question here says that we have a mass of 10 kilograms and a delta v of 20 meters per second. So we have 10 times 20 equals 200 kilogram meters per second. Now, I should warn you that kilogram meters per second are the unit for momentum. Newton seconds are the unit for impulse. They literally mean the same thing, but for tradition's sake, when I ask you for impulse, I would like you to give me Newton seconds. And when I ask you for momentum, I would like to get you to give me kilogram meters per second. It's annoying, but it's sometimes in physics it's tradition, and momentum is a very old subject. It's one of the earliest disciplines of physics, which means it has a lot of like older traditions. Most notably, the fact that the symbol for momentum is a P, which I think must come from some Latin or Greek something, because a P makes no sense for momentum. And probably it's because M was already taken. I don't know. So this is 200 Newton seconds for our impulse. And we know impulse equals area equals 1/2 base times height of the triangle, or 1/2. The base is 5 milliseconds, and the height is F max. And we know because of the work we've done before that this is equal to 200 Newton seconds. So I can solve for F max. My F max is equal to 200 Newton seconds divided by 1/2, 5 times 10 to the negative 3. And I'm just going to run that into my calculator. 200 divided by 0.5 divided by 5 times 10 to the negative 3. Well, that's a lot of force. All right, well, there you go. It's about 80,000 newtons. I told you this wasn't going to make any sense. So that's one of the common problems that people get sort of stuck on in this part of the unit. Are there any questions I can answer about that? Okay, if there's no questions, I'm going to stop with this portion of the session.